get started. Right, what you have here is a pretty standard looking table, and you're going to be using it to find essentially the area under a velocity time curve. And what makes it different? Well, two things make it different. If you look at one number to the next, one time value to the next, do you notice that they go up in different amounts? So for instance, the first rectangle would be 10 units wide, right? Because from there to there is 10, right? And depending if you're going to do the left or the right, and since you've been asked to do the right, they're using this term called Riemann sum, which actually is where I'm going to be starting today. So you take the guy to the right, the key word here is right. So what you would do for the first rectangle is 10 units long, 185 wide. For the next rectangle that starts at 10 and finishes at 15, that one would be 5 units wide, and you're doing the guy on the right, so it would be 319. And you'd keep going. And if you were me, you'd keep going to the end, and you'd do that as your last interval. And the guy on the right would be this number. And you would be wrong, because it tells you there only to use up to 62 seconds. So when you do this question, will you pretend that that last set of data isn't even there? Right. So you're going to have 6 rectangles, but they're going to be 10, 5, 5, 12, 27, and 3. And those are the guys that are going to be the variable widths. And then you're going to use the height of the first one. The second one's going to be this guy. And the 6th and final one's going to be that guy. So hopefully that cures that little problem. So let's now do what I intended to do today. And that is talk about Riemann sums. In particular, how to find the exact value for the area under a curve. The exact value, not an estimate, but the real answer. Well, let's give you the theory of how that's going to work. And it's going to use limits, kind of like what you did in Calc 1. Can you remember in Calc 1, one of the tricks that we used was if we wanted to find the tangent line, we pick the point P and then you pick another point Q, and you make the distance between them get smaller and smaller. So what you did there is you used limits, but the limits were, make delta x become 0, right? Shrink the darn thing in essentially into nothing, right? We're going to use limits to find the area under the curve as well. We're going to do the limit a slightly different way, but that's fine. So this is going to be a completely general question. So there won't be a number in sight. Suppose you have a curve y equals f of x, and it's going to start at A, and it's going to finish at B, and you're going to split it into n strips. So I would like to generate a formula for, what shall I do? Rn, I think, yes. For Rn. Now let's see what we can do. Well, I'll need to know what delta x is. And delta x is going to be B take away A over N. And I'd like to create my table. Well, normally you've got numbers, so creating the table is a lot easier than it is going to be now. But I'm still going to try and do it as a general thing. So the guy that we call x naught is A. It's an easy one. So this guy here, I'm going to call him f of x naught. Now, this second fella, this one here, he's going to be A plus delta x. And that guy is going to be called x1, and he's going to be a plus delta x. And this fellow is going to be called f of x1. Are we good? Right, if I do the next one, because I'm trying to build a pattern here, would you agree that this would be a plus 2 delta x's? Because basically you take this number and add another delta x. So this fella would be a plus 2 delta x's. And I'm going to call this guy f of x2. Now I want you to imagine I kept on going. And I got to some random guy, which I'm going to call xi. Could have called it xk. I'd actually prefer xk, but never mind. Xi. It's not the second or the third, it's the ith one. Now, if you look at this pattern, x1 is this guy, x2 is this guy. Do you see that xi would be a plus I delta x? And we'll call this guy f of xi. And then the last guy would be b. And if you do n strips, isn't this guy called xn? And couldn't b also be written as a plus n delta x's? So I've tried to generalize the process of taking a curve and breaking into strips. Because I have to generalize it, because we don't know what the function is, we don't know what a is, we don't know what b is. I mean, we pretty much don't know any specific values. Isn't everything very general? N strips, a and b, some function you don't know its value or its expression for. But this is what our table would look like. Now, if I asked you to find ln, wouldn't the answer be delta x, the value of the function at x0, plus the value of the function at x1, and finishing all the way at the end with the value of the function at xn? Are you comfortable with this formula? Right, it's just a general formula. I'm calling this R, my apologies. I should have called it Rn, there we go. Are we good? Still with me? Now, see this fella here, just writing them down on his own. Doesn't that guy, that formula, represent the general value of x in this table? Right, the ith position, if you prefer. So what I'm going to do now is I'm going to take this expression and I'm going to use what is called sigma notation. So it's going to be delta x sigma, which is Greek for, well, in this case, it's the capital sigma. And basically, it's going to add these guys up. So I'm going to add these guys up by calling them I equals 1 to n f of xi. That notation is the same thing. Did I put 0? I did, didn't I? If you're doing the right one, you don't use that term, do you? Remember, when you're doing the right hand, you start at 1. So I accidentally put that guy in. That's it better now. This fella is also Rn. These are called Riemann sums. Now I'm going to bring that delta x inside because it just looks nicer there. We got that guy. Last, or second last thing. Instead of xi, I'm going to write that guy down. And this weird looking thing is how we are going to find the exact value for the area under any curve from any start value A to any finish value B. What this is saying is that these all represent, these two guys together, represent the area of one strip. And in this sigma from 1 to n, we're doing n strips. So how do we expand that to find the exact value? Well, that's where the limits come in. Because the exact value of the area is simply just the limit as n tends to infinity of Rn. Does that make sense? That if you took an infinite number of little strips and added them up, wouldn't that be the area under the curve? And you will very often see it written down a little bit more precisely. Instead of Rn, we write this thing down. Are we good? Now, question 10 has a video where they go through a lot of what I've just done. And your answer is just true or false, so it won't be taking you that long to do the answer part. But let's keep this guy and just call him the area. And it's the limit as n tends to infinity of the Riemann sum. We're going to calculate some of these weird infinite limits. Not pretty, as you can imagine. We don't do it very often, because once we've done a couple of them, we are going to say, hey, wait a minute, I see a pattern here. There's a much easier way of getting this answer, and that is going to become basically our shortcut for getting the area under a curve. So we'll have a little shot at playing about with these, hopefully not too many questions, and then we'll jump straight into the shortcut. Now, for notation, isn't that the notation that we would use for the area under a curve between A and B? Now, if you look at this bit and you look at this, you might be able to see some kind of connection. Isn't delta x times f a bit like f of x dx? You see those two terms look very similar. And this integral symbol, well, doesn't really belong much, but it's to do with the sum, essentially. So this notation isn't as weird as it might have looked just now. So I guess I'm looking over at my questions here, which is why I'm a bit distracted. This is question 11. We're being given a function f of x. It's x squared e to the x, and it's going to be from 0 to 3. And what we're being asked to do here is kind of complete the Riemann sum limit. You can hang in there if, darn it, my little thing's going weird on me. There we go. I'm just going to this thing and putting in the solution so we can see it.
What does the I equals 1 mean?
I equals 1 means you start at, since I'm not using this fella, you start with 1. So I equals 1 means the first time you do the sum, I is the number 1, so you generate this guy. Then you make I equal 2 and you generate this guy. I equals 3 would generate the third guy. The variable I is just like a counting variable. It allows you to start at one end of the shape and move to the strip at the last stage. So if I said I was 7 here, I'd be looking at the 7th strip, right? The delta x and the value of the function at the 7th position.
Oh, that makes sense. Thank you.
Now, I'm almost there. I had to go up and change some things to make it Now, we want to do, this is what we're being asked to fill in. I think it's going to be easier if I just write it and then do it here rather than jump back and forward. And that bit they give you, and our job is to fill in what this stuff would look like. So we don't need to worry about those two. They're in the question. Our answer, which I think I'm going to write in red so you know what the answer looks like, is to fill this stuff in. So you might think, from what I've done, that you would just say delta x, f of a plus I delta x every single time, and that would be it. Well, nope, they want a little bit more than that. So here is some of the things I'm going to have to calculate. I'm going to have to calculate who delta x is. Well, at least I've got some stuff to play with. Would you agree that A is 0 and B is 3? So that's going to be B take away A over N. That's going to be 3 take away 0 over N. That is going to be 3 over N. Now, you wouldn't write this down, but I want to do this one really slowly. So your answer might be, oh, all you want me to do is to try and put a little bit more detail into this formula. So instead of delta x, I'm just going to write 3 over n. Okay, that's a lot better, but that's still not what they want. Can you see anything else that I could play about with here? Anything I could replace by something else?
The delta x within the f of x.
Okay, so I equals 1 to n. 1 is n tends to infinity. So I've got a 3 over n. I have an f. I have an I. 3 over n, which is a bit messy, but I'll fix that later. Is there anything else I could fix in this? Change for something else?
You could put in A.
And what would I replace the A with?
Well, it wouldn't really matter, but 0.
Right. Well, it kind of would, because it would make it nicer, wouldn't it?
Yeah.
Now, this is not the finish either, but this is getting much closer to the finish. And I 3 over n, I think, doesn't that look nicer if you write it like that? So far, so good. Now, is there anything else, really, that I could turn that into something different?
You could plug the 3i divided by n into the actual equation.
Up here, you see it?
Yeah.
And that is the answer. So you took the general formula and everything and anything that you can rewrite, you know, using A's or B's or numbers or powers or functions, whatever, you should do it. So your final, I promised red, didn't I? So your final answer is this fella here. Is that okay? Times 3 over n, that's what x is, right? That's essentially your x, right? 3i over n squared e to the 3i over n. Right, so I think we've went from one extreme to the other. Doesn't that number crunching from yesterday seem a whole lot simpler now than what we had to do here? And isn't it? And that's what they're wanting. So that would be the answer to question 11. And question 12 is very similar. And now we're going to look at question 13. So I'm going to start with the general version, which is this fella. And in question 13, we're being given the function, and it's y equals x cubed. And we're going to be doing it from 0, which is a, to 1, which is b. And here it goes. It's going to be the limit as n tends to infinity. Well, first thing I'm going to do, like I did last time, is find delta x. And this time, b take away a over n, it ends up being 1 over n. So it's going to be this fella. Delta x is going to be 1 over n. This function here, isn't this going to be f of 0 plus I times delta x, which is that guy. So it's now going to be the limit as n tends to infinity. That guy, which is now going to be right, I over n is this guy cubed. So what's that going to get me? It's going to get me 1 over n times I over n cubed. So far, so good. Are we good with this, guys? Okay.
Yeah.
Okay. I mean, this is heavy duty, I don't know, algebra, I guess. If I make it a little bit prettier, would you agree that I get I cubed over n to the 4? And normally that would be the end of this question, but we are going to take it further. And you might think, nope, I don't know how to find an infinite limit to something that's been added up. I've never seen that. But you're going to get some help. First thing I'm going to do is use a property that you're allowed to do with summation sigmas. If the term on the bottom is a constant, and n is a physical constant, I know it later on goes infinite, but right now it's a physical constant, you can suck it out of the sigmas. And so this is the same thing as that. Now, wouldn't it be nice if someone could tell me what this fella here was equal to? Wouldn't it be nice if they did that? And the answer is, if you read the question in question 13, that they tell you what this is equal to. And this thing here is equal to n plus 1 over 2 all squared. Now what I'm going to do is going to work on this. It's 1 over n to the 4 times an n squared times an n plus 1 squared over 4. I'm then going to cancel out a little bit I'm going to have n plus 1 squared over 4n squared. So from this line to this line, I just cancelled an n squared. By the way, this is the only time I'm going to do a question like this. Can you understand probably why? They are horrendously long. But I cubed is this because the question told me. This, if you square it out, gets you that. This n squared cancels partially with that n to the 4, and then to combine the bottoms, you get that. If I FOIL out the top, we get that. Haven't we finally reached a place that we actually know what to do? What's the limit of that going to be? How will we find it?
It's the first terms, right? The
Yeah, you
n
can
squared
divide.
over 4n squared.
Yeah, so you can divide. The technique I would use is divide top and bottom by n squared, but L'Hopital would work if you wanted to use that. And so that's going to be the limit as n tends to infinity of 1 plus 2 over n plus 1 over n squared all over 4. Can you remember Calc 1 doing limits? This is essentially bringing that skill back again. And when you brute force it, you get 1 plus 2 over infinity plus 1 over infinity squared over 4. And all that hard work, that is the exact answer to the area under the curve y equals x cubed from 0 to 1. Now, if we had to find the exact value for the area under the curve using this technique, I think you would probably change careers. It is not a very pretty technique. It's clunky. You have a lot of things to do. And actually, it's not that practical. Can you imagine that you could probably only do this for very simple functions? You know, x squared, 2x plus 1. You couldn't do it for anything really ugly. But nonetheless, it was a good starting point, and it does mean that we have a technique for getting exact values for the area under a curve. The Riemann sum method. So what I'm now going to show you is some questions where you're going to basically just fill in the missing stuff, but you're not going to do anything else. So it's going to be a lot easier than that question I just did. That's like the worst one you could do. So I'm going to nip over to the homework because I've got the answers set up there. And I might make it a little bit bigger. Scroll down to where we are, right? Right, that was question 11. Remember the one we did a minute ago? That was this guy. That's what your answer looks like. You just plug it in here, right? If the function is 9 plus sine squared, and you're going from 0 to pi, can you recognize this little guy at the end is delta x? And then if you do 0 plus that guy, and then you replace this x essentially, you see that x becomes this. So the expression gets turned into this, and then you finish with whatever delta x is. That's the guy I just did a minute ago. Right, this one a little bit trickier, right? If you want to find delta x, don't you do 9 take away 2 over n? So that's where the 7 over n came from. And do you see this says 2 plus delta x? Can you see a is 2 and delta x is that? So it's going to be a plus delta x, that's 2 plus 7i over n, and see the x that's there. So you see these two x's get replaced by 2 plus 7i over x. Basically a plus I delta x. And then here is a Riemann sum already set up. And if you know what to look for, you should be able to find who the function is. Well, when I look at this guy here, do you see that the clue is I over n to the power of 4? That's why it's this one. In this question here, can you see that it's 1 over 2 plus this guy? And this guy here is basically delta xi. So that tells me it's a 1 over 2 plus x, right? 2 plus this guy, 2 plus x. This guy is essentially like your x-axis. How do I know it's from 0 to 5 and not 0 to 1?
The 5 over n, the
Yeah.
5 on the top.
Yep, that's it, the 5 on the top. Right, in this one here, can you see A is going to be 1? Can you see that B is going to be 8? And can you see the function 1 plus x? So this guy becomes that guy. That's the rough bit over. We're now going to get the shortcut. We all want to see the shortcut, don't we? Because you've just seen the horrible way that you have to do it if you didn't have a shortcut. So let's make your life 10 times easier. Could I explain 13b again? Sorry, I didn't catch that earlier. So 13b. Oh, in 13b, they're telling you that's true. Right, that's a piece of information they're just giving you. And if you remember back in my notes, I used that to eventually get the quarter. So 13b, the only thing that's your answer is here. And all you would type in would be a quarter. So you are not expected to know that this is equal to that. You're just expected to use that this is equal to that. Oh, and by the way, this is sigma I equals 1 to n of I cubed. That's what sigma I equals 1 to n of I cubed looks like. So that's where that came from. Now, I'm kind of glad that's over. Do you know what it reminds me of? Can you remember when we did delta epsilon in Calc 1? And we kind of did it and said, you know, like, remember epsilon, you know, and delta and all that stuff. It's one of those, it's a theory behind why we do what we do, but really the important part of this is that we can, in fact, get exact values. So I am going to show you some answers. And I'm not going to put any numbers here because that's just a distraction. I'm just going to tell you what the general integral is. If you integrate this guy, that's your general answer. There's a bit that I'm adding onto it, but I'm not going to do it right now. So if you want to integrate a straight line, the formula that you're going to end up using is that guy. Can anybody see a pattern in all these answers?
Isn't it the antiderivative?
That is exactly what it is, but only people who've seen integration before would know that, but you're right, it is. How do you get from here to here? What's the rule? Okay. Suppose it was x to the 10. The answer is x to the 11 and a 1/11th stuck at the front.
You bring the exponent out to the front, they cancel out, and then you subtract 1 from the exponent.
Subtract 1? You sure?
Yeah, from the exponent.
Which one do you mean? You mean you're sounds like you're telling me how to go this way. How do you go that way?
Oh.
Kind of reverse what you just said.
So you add 1 to the exponent,
Mm-hmm.
and then you do the bring it out, and then do the reciprocal.
Yes. So if I wanted to do the antiderivative, might as well use the name of this guy, you would add 1 to the power, and then you divide by the new power. Now you might be saying, well, how is that going to help me? Well, if you want to find the integral from, say, 1 to 4 of x squared, right? The area under the curve of x squared from 1 to 4, you would add 1 to the power, and you would divide by the new power. The reason why it's called an antiderivative, do you know if you differentiate that, don't you get this guy? Antiderivative, the opposite of differentiation. And the notation is a bit clunky, but you do a vertical line and you say, evaluate this expression from 1 to 4. So when you put in the top number, you get 4 cubed. If you put in the bottom number, you get 1 cubed. And that's 4, so that's 64 thirds. Take away 1/3, guess that's 63 thirds, and therefore you get 21. That is essentially how you get the exact area under a curve. So I'm going to spend a little bit of time trying some guys out. So here is the original function, the thing you want to find the area under it. And we're going to put next to it its antiderivative. Okay, here goes. If you had a function like x to the n, and let's say you had a multiple of it, let's call it axn. So that would be like 5x cubed or 2x squared, right? That kind of thing. Then the antiderivative would be add 1 to the power and divide by the new power. And I put an example, totally random. 7x cubed. You would get an x to the 4 and divide by the new power. That would be the guy. Now, I've missed out a thing which you're meant to add here. Whenever
The
you get
constant.
an antiderivative, you have to put an arbitrary constant. Why do you need an extra plus an unknown number? Well,
When you take the derivative of a constant, it goes away. So we don't
And-
know if the constant exists.
yeah, you don't know the value of it. So that's a placeholder. Right. So when we talk about antiderivatives, we always finish with a plus c. And antiderivatives are the shortcut to finding areas under curves. Because what you do is you take the original function that you want to find the area, you get its antiderivative, the plus c kind of loses, it goes away essentially, right? So you find its antiderivative and you evaluate it at the start and finish. Now, if an antiderivative is the opposite of differentiation, then shouldn't we be able to use the fact that we're good at derivatives to figure out what an antiderivative of somebody is? So you have to say to yourself, what function do I need to start with? Right? So what function do I put here? That when I differentiate the function that I put here, I get e to the x. One of my favorite functions. What is the antiderivative going to be?
Isn't it e to the x plus c?
Yep. Suppose I wanted to do the antiderivative of sine x. What function would you need to start with that if you differentiated it, you would get sine x? I'm going to put in the plus c for free.
Isn't
So
it
what?
negative cosine x?
Yes. Do you see why you need a negative, everyone? If you differentiate negative cosine, don't you end up with plus sine? Okay. What would you need to start with then? What's the antiderivative of cosine x?
Sine x.
Yeah. Do you notice that those two guys are kind of the reverse of differentiation? When you differentiate a sine, don't you get a positive cosine? When you differentiate a cosine, don't you get a negative sign? Do you see how in antiderivatives, not surprisingly, it's the opposite of that, isn't it? Anti-opposite. Here's one that will stretch you. What function, right, what guy goes here, has a derivative that's equal to sine squared x?
Tangent.
Say it again.
Tangent x.
It is indeed. What function has a derivative of secant tan x? Oh, that one's got you. Say again.
Sick.
Correct. What is the antiderivative of 1 over x? What function has a derivative that's 1 over x?
Natural log.
Yeah, okay. Is there any functions that I've missed here? Anything you might want to know the antiderivative of that you can't see at least somebody in the family of it?
Square root of x.
Okay. So let's start with this function, square root of x. I would like to get its antiderivative. Well, I'm going to start by recognizing that the square root of x can be written as a fractional power. Great. Square root of x is x to the half. And then I'm going to use something that you might not think works, but it does. See this guy over here, this one? It's got its own name. It's called the power rule. Remember the power rule for differentiation? Right, allowed you to differentiate any power of x you like. Couldn't you use the power rule to differentiate fractional powers? Remember the power rule? You could use it to do negative powers, all right? Really, any kind of weird power. I'm going to use this rule. And this rule, right? If that's f of x, it says add 1 to the power and then divide by the new power. You see 1 over 3 halves is the same thing as 2/3. And that means that the antiderivative, right, of square root of x is 2/3 the square root of x cubed. And we have a rule that's called style points. That's what I call it. And the rule is, whatever your original function is, your answer should look like it. So it's not a good idea to say that the antiderivative of the square root of x is this guy. I know it is equivalent, but we have a little rule so everybody in the universe writes the answers the same way. And I call that rule style points. And what that says is that you should make their answer, right, your antiderivative, look like the original. So if the original was x to the half, that's perfectly fine answer. But if the original was a square root, make sure your answer's got a square root. Does that seem reasonable? How about this function then? Wouldn't it be nice if I could find its antiderivative? Right? It's a guy you might want to find the area for. How do you think I'm going to rewrite this one?
Tan x to the negative 4th power.
Yeah. Now, when it's written that way, can you see that we can use the power rule on it? Add 1 to the power and then divide by the new power. That's how I say that out loud. That's the formula, but I think it makes more sense to think of adding 1 to the power and then dividing by the new power. Now, if you add 1 to that, you get -3. If you divide by the new power, that's the guy you've got. And then style points kicks in. That's the original. Oops. That's what the answer should look like. So just to finish with, if you told me you wanted to know the area under a curve from 0 to pi of, let's say, sin x. So what would that look like? If you wanted to know that guy, right? If we were doing it earlier today, wouldn't you just do 20 strips or 40 strips and you could give me an estimate? The Riemann sum technique doesn't really work on sin x because it's too complicated. But the shortcut, the antiderivative, works really well. The antiderivative of sin x is negative cosine x. The plus c we don't care about. And the reason the plus c doesn't matter is that both of them have a plus c and you're going to take the first number away from the second. So they essentially cancel out. So we call this guy, the notation is from x equals 0 to pi. You plug in the first one, which is the cosine pi, right? Subtract, so it's always first guy, take away the second guy. Cosine pi is -1, so the negative of -1 is 1. The cosine of 0 is cosine of 0
Is 1.
1. So that's -1 because it's negative cosine, but then you're subtracting it, so you get 1. Are you amazed by how nice that answer is? And since I have all these lovely antiderivatives, can't I find the area under any of these curves? From any start number to any finish number, as long as there's not some weird vertical asymptote or something going on.